Hey all, back for a round of physics, I see. And today we're going to try something a little bit different here. As you see on the screen, we have Excel pulled up, and I thought today that we would actually just sit down and discuss for a brief moment about how to actually go through and use a computer to actually do the physics for us. So this is sometimes called numerical integration. This is sometimes called computational physics. But the whole idea is to use the computer to solve an equation numerically. So rather than going through and programming in terms of variables and telling it, this does this, and then have it come up with an expression in terms of variables, it just brute forces it. In other words, it just plugs in numbers and brute forces it. So it's a really interesting technique, and it's one that can be very useful in the future, particularly when you run into forces that are not particularly nice, these mean forces. So let's get an idea. Let's go at this. So before you do some computational analysis, you almost always have to set up some parameters. And so here I'm going to set up some parameters just in column A and B. Column A will serve as the label, and then column B will actually be the values. And one of the most important parameters that we're actually going to set up is what I'll call delta t, our time interval. And this is done because I want to tell it how many seconds I want it to elapse between its calculational steps. So right now I'm going to do delta t. Why don't we try to see, for example, let's model projectile motion. We'll start off there, and then maybe we'll work into a little bit more of a complicated situation. So that being the case, let me set some other initial parameters. For example, let me set an initial height. So we'll set this up, and right now I'll leave it as 0, although we could later vary it to whatever we want. And well, let's see. Let's say we have some initial velocity, so I'll call that v0, and again we'll put in just some random value here. And lastly, maybe a launch angle, so I'll put angle here, and put it as 30 degrees. Actually, excuse me, I think Excel, if I'm not mistaken, actually does radians for its measurement. So we'll do 30 degrees, that's pi over 6. Oops, equals pi over 6. There we go. So something like a launch angle. Okay. Now, the next thing I'm going to do in these columns over here, I'm gonna actually label some stuff. Y, time, y, x, y. And the whole idea here is that I'm going to have a bunch of different columns with calculated values in them. And so I want to label these columns something like V0 in the x direction, maybe V0 in the y direction. And then I'll put here a force. So I'll put force, net force, maybe a better way of doing it, force. And then maybe something like an acceleration. And then I'll do V final in the x direction, V final in the y direction. And then we'll put in x final and y final. So just some breaking down exactly what we're talking about here. You see in the first three, the time column, just how much time has elapsed. Initial position in both the x and y direction, the initial speed in the x and y direction. And then after that, based on these four parameters, the position and the speed, we should be able then to determine the net force acting on the object. Once we have the net force, and maybe we need a mass of an object, so that might be another one that we need to include here. Once we have the net force and we know the mass on the object, we can figure out the acceleration. Once we know the acceleration, we can use that to find the final speed in the x and y direction. And then lastly, in fact, maybe scoot that over, I'll say ax and ay. Once we have those accelerations, then we can find the final speeds. Once we have the final speeds, we can find the final positions. So this is the basic structure of mechanics. If you know the initial position and velocity, and you know the forces, you can find the initial velocity or the final velocities and the final positions. So we're just following along with this. Thinking of other parameters that we need, let's go ahead and put gravity in as well. So what we're doing here is I'm programming in, and later on you can vary these parameters, and the Excel sheet should just automatically update, which is pretty cool as well. Okay, now let's say T0. I'll start a starting time, I'll put it as 0. So the first thing I'm going to do is, you notice I'm going to start by a time, and here I'm going to reference cell B2. Okay? So in other words, I want my starting time to be 0. Just kind of simple. Let's start our thing at the origin. So in some sense, you could put an initial position in here. Maybe we should do that too. So height and position. And we'll say that it starts at 0, 0. So it's starting at the origin. So we'll say position is equal to B3. So you see how I'm using those initial parameters to actually start out with. I'll call this B4. Now here we have an interesting one. If we remember our triangles and how to relate the speed to the component of the velocity to the angle, we can go ahead and we'll put in B5 times cosine of B6. So you see B5 being the speed, B6 being the launch angle. So we go ahead and put that in. And of course here we have same thing, B5 times the sine of B6. Yeah. We got those. Now, for the first part, let's just assume that we have the gravitational force acting on us. And so we'll do something like B7 times B8. Okay, just the gravitational force. Okay. And then, oops, actually, maybe I should do this, excuse me, as I'm building this, I'm thinking of more things to add in. Why don't we say the force in the x direction and the force in the y direction? Ooh. Okay, so you notice now I have 2 columns for each of the characteristics: initial position, initial speeds, forces, final speeds, or accelerations, final speeds, final positions. So some of this is a bit creative in the sense of I'm building up additional things as we go along. So gravitational force is only in the y direction, so we'll put B7 times B8. Okay, enter. And now here, this latter half from K through P, we're going to reference the quantities that we have in cells E through J. So these cells will be filled in based on these cell values. Okay? So for example, the final acceleration in the x direction would simply be I2 divided by the mass, B, and I'll put $7 here. Okay? Or for example, the acceleration in the y direction will simply be the value in J2 divided by $7, the mass again. Okay? Now we have to think about it, but once we have our acceleration in the x direction, we can find our final speed in the x direction. That is simply the initial speed plus the acceleration, k2, times the time interval, which is our delta t, $1. Okay. So I'll say that again. The final speed in the x direction is the initial speed plus the acceleration times the time interval. So we're just using the definition of speed or acceleration here. You can do the same thing. If you want, pause a minute and see if you can come up with the expression for this one. We'll go ahead. So the final speed is the initial speed, h2, plus the acceleration, L2, times our time interval, $1. Okay. There we go. So now we have our final speed. Oops, excuse me, I used E2. It should be G2, right? Yeah, there we go. That's better. Yeah. You always got to catch yourself. So let's go ahead. How about the final position? So if we think about how speed and position are related, say give yourself a second. Okay. If you remember, this is the definition of average speed. So what I'm going to do here is I am going to say, okay, well, let me take M2 plus G2. Okay. So I'm summing the 2 speeds and then taking an average. So there's the average speed, and I need to multiply that by my time interval again, B1. And I need to add to it my initial position, E2. So I have, again, average speed, M2 plus G2 divided by 2 times my time interval, B1, plus E2. Okay. There we go. There's our X final. And we do the same thing. Pause the video, take a second, see if you can come up with it. I'll go ahead and write this in now. H2 divided by 2 times $1, time interval, plus our initial position, F2. Okay. There we go. Pretty cool. You see that it's moved in both the X and the Y direction. Now here comes the magic sauce. Okay. The interesting thing is that all of these final quantities, these final positions, and these final speeds, we want to set that as our new initial conditions. Okay, so what is this? 1/100th of a second has elapsed. These are our new initial quantities. So what I'm going to do is I'll go down here. I'll say, okay, well, this is equal to D2 plus 1 time interval, $1. There we go. Here, I'm going to set this equal to O2. Enter. This will be equal to P2, enter. See, so now I'm taking those finals and I'm using them as the new initials. Same thing, equals M2, enter, equals N2, enter. Pretty cool, huh? Now, here, go ahead and since my force stays constant, I'm just going to put I2 here, equals I2. Put equals J2. Okay. And now I will use, now here's the magic about programming in terms of those cell references. All I'm going to do here is I'm going to click and drag down. And now we should see that indeed the acceleration in the X direction is this new value, I3 divided by mass. Yeah, that looks good. Okay. It's always good to check. J3 divided by the mass, that's good. So now I need to use the initial speed plus the acceleration times the time interval, so that's good. Same thing, the initial speed plus the acceleration times the time interval, looks good. We have our average speed, so G and M, okay, divided by 2 times our time interval plus E2, okay. And same thing, let's take a look. Yeah, H and N divided by 2 times the time interval. Yep, times F3. Good. Now I should note one thing if you're not familiar with it. You probably noticed that I used a $sign here. So instead of saying B1, I used $B1. And there's a very specific reason for that. So when you do this click and drag process, so if I just put B1 here and all over here I'll put $B1. When you do this click and drag process, you'll notice a distinct difference when I do this. Okay, so you notice when I did B1 as versus $B1, after I click and drag, you notice a weird thing going on. Namely, the right-hand column, or the left-hand column keeps changing in values, whereas the right-hand column stays the same. Okay. What the $sign does is that it tells Excel, hey, when you click and drag downwards, don't change the cell reference. So you notice this says B1, that's the top one, but if I go to the next one, it also says B1. And again, B1, and as you go down, you notice that all of them say B1. Okay? And you notice the $sign prevents it from changing. Over here, you notice if it's B1 and I clicked and dragged, the next one is actually B2. And the next one's B3 and B4, B5, B6, so on and so forth. Okay? So the $sign prevents the, how would I say it, changing the row automatically. If you put the $sign before the row reference, then the row reference never changes. Okay? Similarly, if you wanted to do something for completeness, let me mention this as well. You could do the same thing if I said B1 and I said equals $B1. $B1. Okay. So now instead of putting it in front of the row reference, I put it in front of the column reference. So then if I decide to click and drag sideways, you'll notice that the one that does not have the $sign keeps changing, right? B1, this next one will be C1, so you see, D1, E1, F1, et cetera, et cetera, et cetera. So that changes. Whereas here, you notice because I kept the $sign in front of the column reference, it continues to stay the same column, B1, 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 B1. Okay. So that's what that $sign does. It prevents it from changing depending on what you put it in front of, either the column reference or the cell reference. Now, since I'm clicking and dragging downwards, I want to put it in front of the row reference to make sure that it doesn't accidentally pick out a new mass, for example, as I drag down, or it doesn't accidentally pick out a different time interval. Okay. Now we should be all set. Now that we've got our second row all established in here in terms of variables. So the first row had those parameters in for the first 5 or 6 columns, and then we had to program in the second set of columns. This one is all in terms of variables. So now the magic happens. We just simply click and drag. You can go as far as you want. Essentially, the limit here is how much space your computer has, how many calculations your computer can handle doing. So if you want to do 10,000 or 50,000, the sky's the limit. Okay, so roughly 500 here. Okay, that's good enough. So let's get an idea of what's going on here. So now it did all the calculations. Let's see if we can plot, say, the final position, a scatter plot of the final X position versus Y position. So we'll go ahead and throw this in here. And you see right away, something looks strange here. Okay. So it looks parabolic. In fact, we could fit it. Let's go ahead and fit it. Let's see what the best is. Let's say polynomial of order 2. Display equation on chart. Display at Y. There we go. Okay. Close that down. And we see that, yeah, indeed, it is a quadratic. Okay? In fact, R equals 1. Okay? So this produced a quadratic, even though you notice in the program I never told it that it was supposed to be a quadratic. But there does seem to be an issue here, and we have to figure out what that is. And the first thing we notice is that as time progresses, my Y final never turns around. And there's a hint right there. And the hint comes back down to, oh, shameful, I forgot to put a negative sign in for my gravity. Okay, well, so either we could modify it up here, or the other simple way to do it is, let me just put a negative 9.8 in right here. Okay. Now you notice the gravitational forces are negative, and wham, all of a sudden my chart changed, which is pretty cool. So, awesome, 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 awesome. Let's go ahead and zoom in a little bit. So the issue here is let's go ahead and zoom in to say 20. Get a sense of what's actually going on here. Can we actually see the projectile motion? And it seems that indeed we probably can, but we just need to give ourselves a little bit more. There we go. So we were just zoomed out so far that we couldn't see it, and there we go. Right, you get this nice parabolic path, even though, again, when I programmed it in, I didn't say it was parabolic. Now, of course, so that's the first thing. Now, the other nice thing about doing this in terms of parameters is I can change the mass of my object. So, for example, if you're not sure your computer program's working correctly, we could always go ahead and double check some things. Like, for example, during our whole discussion about projectile motion, we never once mentioned mass. It's because the mass of the object doesn't matter. So let's go ahead and see here. I should be able to change the mass, and the shape of this trajectory should stay the same. And you notice I'm doing that. You notice that this column is automatically updating depending on what value I put in here. But at the end of the day, you'll notice the path doesn't change, which is what we expected. We can do other things. Like, for example, let's say that I'm on a cliff, a 70-meter cliff, and I want to project it this way. And all of a sudden, you see that now I'm up higher, and maybe I should actually, let's go ahead and change out the axes here. So I've restricted it, let's say 100 now. So we've got to change that. And now we see, oh, yeah, indeed, it follows a parabolic motion and it lands, which is pretty cool. Or say you want to change the speed. So it shouldn't go as far. This is about 35. Let's say we cut it in half. It shouldn't go nearly as far, specifically half the distance. And you see that the chart automatically updates for us. So that's all pretty cool. And in fact, we could also change the X position, say that you launch it off a cliff, but it's 10 meters away. So we can shift that as well. Okay. The other one that we can change is delta t, so we can actually fit in more data points if we want. This one might crash my computer. Let's hope not. Cool. Okay. So you notice the path didn't change at all, which is what it shouldn't change. So that's just one way to actually go through and do some of the computational modeling. I'll go ahead and stop this here. We'll start picking up a more difficult situation in a second. So let's go ahead and let's get an idea about how do we incorporate forces that aren't quite as nice into a program like this. So one of the first ones that I'll think about is let's see if we can include something like air resistance. Now I'll pop up the equation for air resistance here right in front of you, and I'll just go ahead and describe what some of these variables mean. So the force of air resistance, you'll first of all notice, depends on the density of the fluid that you're moving through. That's represented by this Greek letter rho. So that's the density of the fluid. In this case, we'll use air. It has a density of something like, I want to say it's about 1.2 kilograms per cubic meter. So we'll go ahead and use that. I'll set it up as a parameter, so if we decide to change it at some point, no problem. C represents the cross-sectional area of the object. You know that, for example, if you put your hand out the window and you leave it like this as you're driving down the highway, you don't feel as much of a force on it as if you just put it up, right? You roll down your window, you put up your hand like this, it's going to go back really fast, whereas I always like driving down the highway. You drive down the highway with your hand out the window just nice and flat, you can kind of slipstream your way through it. So C represents the cross-sectional area of an object, and unfortunately you just have to go and look that up. Okay? So it depends. There's a lot of, for example, if it's a car, that number is well known because there's, you know, wind tunnel tests, or if it's an airplane, that's well known. If it's something like a geometric shape, then there might be a theoretical model for the cross-sectional area, et cetera, et cetera. V squared is what you would recognize, this velocity squared, and V hat represents the direction of the velocity. So you're probably familiar with all of those already. Okay? So let's see if we can actually hack away and get an idea about how to include that force in this spreadsheet. Okay? So we've already introduced some extra experimental parameters, so I'll go ahead and put that in right now. We'll put density, and let's go ahead and put a 1.2. Okay. Cross-sectional area, so I'll put cross area. We'll put something like 1 just for kicks. Okay. And now let's go ahead and think about how to modify this. So the first thing that we need to do is we need to look at the force in the x direction. And per the equation that we actually have here, I should now write this as negative, so now we have to be a little bit careful, negative 0.5 times $2, right? The density of air, $10, the density of air, times $11, the cross-sectional area of the body. I'll go ahead and put that in, put the enter in, but we're not done. Next thing we need is the velocity squared. So I better do that. That's g2 squared plus h2 squared. Right? The magnitude would be the components and individual components squared and added together, and then I take the square root. But since I need v squared, the square root and the squared cancel, and so I end up something like this. Good. Now the tricky part. I need the x direction. I need the component in the x direction. So we keep going. So now I need to multiply this by the value of g2 divided by parenthesis g2 squared plus h2 squared to the 1/2, to the 0.5. Right? You say, where did you get that at? Well, let's think a minute about how we get the unit vector. We take our vector and divide it by the magnitude. Okay, that is the unit vector. But then the next thing is I just want the x component of that unit vector. Okay. So that means I take gx, the x component, divide by the magnitude. That gives me the x component of the unit vector. Let you think of that for a second and look at the equation that I have written down here. Okay. Now, of course, there's other ways to simplify this. So you could say I've got a g2 squared plus h2. Let me hit enter first. There are ways to simplify this. You have a g2 squared h2 squared to the 1/2 power in the denominator. You have this guy in the numerator. So you might be able to write, you could prefer to write this as the to the 1.5 power. That might make it look a little cleaner, right? To the 1.5. And that'll allow me to get rid of this rigmarole here in the denominator. So let's go ahead and do that, just to make it look a little cleaner. That's weird. Why did it not look the same? Oh, yeah, not the 1.5. Should just be to the 0.5. Hi. 1 minus 0.5 is not 1.5. Yeah, there we go. Let's try that again. There we go. So you see that nothing has changed. Same number. Now we got to be careful here. Note I put the negative sign in, which means, let's see, if it's moving upward or to the right, then if the ball is moving to the right, that means the force is pushing to the left. So I get a negative sign. Okay. Now we have our gravitational force. We have a gravitational force, and we need to add to it the y component of the air resistance. So let's go ahead and do that. So the first thing is we have to be slightly more careful here. Yeah. So the acceleration is always downwards. The acceleration will always have a negative sign. Let's go ahead and write in the rest of this. So we put negative 0.5 times the air density, $10, times the cross-sectional area, $11. 11. There we go. So 0.5 times the air density times $11. And then we said, hey, we need to multiply this by G2 squared plus H2 squared, H2 squared. We need to raise that to the 0.5 power. Okay. And we need to multiply that by H2. Enter. Okay. So again, gravitation, force due to gravity. Okay. And then we have the force due to air resistance right here. Okay. So hang on a second. Okay. So I think we're looking good here so far. We've got the force in the x direction. We've got our force in the y direction. Okay, which means the chart automatically updated. You notice the acceleration in the x and the y direction, et cetera, velocities, final speeds. Okay, now we have to drop down to the next line, and you notice that the next line, originally I just cheated. I said it's equal to I2, but now I should probably take these two lines and I should click and drag them down so that now you see that they've changed. Okay. And let's go ahead and do that for the rest of the chart. Oops, excuse me. There we go. Paste. Ah, haha. There we go. Let's go ahead and do this a little bit more. And so now we notice, so hey, always good to troubleshoot here. What's going on here? You notice, okay, so it looks kind of funky so far, so we gotta figure out what's going on here. Always part of the troubleshooting process. Always, always, always. So let's see here. Let's make sure that we're now referencing the proper cells. Yeah, looks good. Looks good. Okay, so our acceleration's still downwards. Looks good. Looks good. Okay. 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 Go ahead and pause here for a second. Let's see what we can. Oh, sorry. Brief moment. Finally found it. So we always have to be careful here. So right here, everything's all fine and dandy. You notice I got a B7, B8, but you notice I forgot those stinking dollar signs right there. So when I actually clicked and dragged down to the next one, you notice now it's B8 and B9. That's not how it should be. Shameful, shameful. So I didn't even follow my own instructions here. So let's make sure that I didn't do that for this one as well. B dollar dollar. No, everything looks good there. Dollar 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 dollar. Okay, there we go. So now we might be in a position where we can actually take this down the whole way. Now, ha ha ha. Yahtzee! So we notice, let's go ahead and take this trend line off. So first of all, we can check to make sure everything's going okay. Let's, how do we get that trend line off? Oh, okay. So one of the first things that we can double check on, we make sure stuff is going okay here. Let's get this position off. Okay. Let's go ahead and set the density equal to 0. So if we set the density equal to 0, we should recover the initial projection that we thought we should have. There we go, as you see. So let's go ahead and let's take this up to 20, something like that. Now, the cool thing is as we put in our air density, now we should see a dramatically different shape. And it's pretty cool. It looks kind of odd. Let's start this at 0. It looks really odd. Should figure out a way to resize that, sorry. Because it does get like a pain in the rearish to actually, let's see, do this over and over again. How do I get rid of that stinking trend line? Should be able to just click on it. There. Oh, okay. So I apologize. Seems that I had that trend line selected, but because of how I was actually zoomed in, I couldn't tell that I actually had it selected. So here we go. Okay, so back to the ideas that we're dealing with here. If I go ahead and I put in something like this, you notice that we have, let's say 20. You notice I have a nice parabolic arch range equation just going the whole way. And it's always interesting because you notice if I add the effects of air resistance, say something like 0.5, which is half the density of the air, you notice the dramatic difference that you actually see here. I mean, I'm always fascinated by it. That's huge, right? I mean, we went from a projectile over 40 meters, and I put in an air density of 1.2, and all of a sudden it's going less than 3. Just, I don't know, that just baffles me in terms of how much of an effect air resistance actually has on an object. So that's the first thing. And second of all, you notice, for example, if I zoom in here, and again, I'll stop zooming in and out so much, but if I zoom in here to say 5.5, you'll notice that, or maybe I go 5.2, something like that. You notice the other interesting thing is that the path is no longer symmetric, right? You notice that it tends to be more quadratic at the beginning side, and then when you hit the peak, it kind of flattens. I mean, this air resistance has a tendency of moving the peak to the right on this projectile. So that's also kind of interesting. It breaks the asymmetry. Of course, if you launch it from a higher height, say that instead of launching it from ground, let's launch it from, say, 5 meters, you notice a third really interesting thing is that in addition to it flattening out, you'll also notice that it almost tends to move straight down near the end. And that should make some sense. This x component, the force in the x direction, just continually slows it down, keeps slowing it down. And if it's a long enough trajectory, indeed, eventually the forward, the x direction, the horizontal direction, will become 0 and it'll actually fall straight down. So it'll just bleed speed away in that horizontal direction. And if we actually looked carefully enough, if we could actually see it in this model, you'd also notice that the y component will be equally spaced. Now maybe we can see that down here. You notice, okay, so this is negative. Oh yeah, okay, so that's good. So it's turned around now. Now, of course, it's below the ground, say 200. Let's see if we can find some spot where it's still above the ground. Okay, so yeah, right here. That's fine. You notice, okay, so it's still above the ground. It's about 1 meter above the ground. In fact, right here, after 2.3 seconds is actually where it finally hits the ground, right? You get a negative y value, and so that means it hits the ground. But let's take a look at some of the speeds right before that. So here's the speed column. Let's see, position in the y, position in the x, speed in the y, speed in the x. So let's go ahead and take a look at some of these columns real fast right before it actually hits the ground. You notice the speed in the x direction is 6 centimeters a second. right? I mean, like that's 0.06. So it's essentially stopped. It started out something like, I don't know, like 8 meters a second, and now it's down to 6 centimeters a second. So it's essentially stopped in its forward direction. The other interesting thing that I noted is that here in the y component, you notice that the speed in the y direction is essentially constant. It's negative 4 meters per second. Okay. Now this is an effect, you'll talk about this in lab, but this is an effect called terminal velocity. What's going on is the moment that the object hits its peak and starts falling downwards, the force of gravity is still pulling it down. So that would cause it to want to accelerate downwards. Because it's moving downwards, though, the force of air resistance actually starts pushing up on it. Okay? Air resistance is always opposite the direction of motion. So if the object's falling down vertically, that means the air resistance is pushing up on it. And so what we're noticing here is that eventually the acceleration in the y direction, which I have, let's see, position, speeds, oh, here's the acceleration in the y direction, essentially goes to 0. Okay? At some point, the speed is fast enough going downwards that the air drag, the air resistance, the force of air pushing upwards equals the force of gravity downwards. And we'll go ahead, I'll put a little byline in. We can figure out exactly what that speed has to be for a given object. But here, you can see it just numerically that the acceleration essentially goes to 0. It's negative, let's see, it's up here, this is 1 centimeter per second squared in terms of acceleration. And eventually it drops down within a couple of tenths of a second. It's down to millimeters per second, 8 millimeters per second. That's just pretty low. Okay? So that's pretty spiffy in its own right. Now again, you can use this to actually solve just, whatever. If you want to do a cliff launch problem, you put your height to 70, and there's some fancy ways that you could actually do this graphing just to make sure that it always shows up. But for right now, we'll just do it like this. We'll just manually change it. You'll just have to forgive me for having to keep doing this. So say you want to do the cliff launch problem, you can actually figure out, for example, visually, when does it actually reach the height that it was launched from. So all you have to do is go down here and say, okay, well, when does this value, and there's some fancy search functions that you can do as well, when does this value actually equal 70 again? And you see that it's about 2.87 seconds after its initial launch, it returns to its initial height, and it's 40 meters downrange now. Anyway, so I'll leave it there for right now. Thank you for your attention. I'll see you next time.